Now we're going to continue with Chapter 14, and we're going to look at 14.4. We're going to look at crown ethers. Now, an ether can interact with a metal ion. Okay, and that metal ion either has to have a full positive or a partial positive. Now, a Grignard reagent, which is a special type of organometallic, and it's used to make new carbon-carbon bonds, and it's thought to act as a nucleophile. It's formed in the presence of diethyl ether. So in order to make a Grignard reagent, we have an alkyl halide. We're going to add magnesium metal in diethyl ether. And we will get our Grignard reagent, where the magnesium inserts itself between the R group and the halogen, and the lone pairs on the oxygens of the ether will coordinate to the metal, which has partial positive charge. And this can go on to form new carbon-carbon bonds. And we'll look at this reaction later on. Because the magnesium has a delta positive, this carbon has a delta minus, and the negative carbon can react with a nucleophilic carbon. With an electrophilic carbon. So the carbon that would have a delta positive. So this will act as a nucleophile. And we'll look at some reactions of Grignard reagents with epoxides in a little bit. Now, a scientist at DuPont named Charles Peterson discovered that interactions between ethers and metal ions is significantly stronger if you have multiple ether groups. So if you have what's called a polyether, so where you have multiple ether groups, you can increase the strength of the interaction with a metal. These cyclic polyethers were known as crown ethers, and Peterson coined this term because their molecular models resembled crowns. So these compounds contain multiple oxygens, and the oxygen atoms point inward and will bind or coordinate to a metal. In naming a crown ether, Peterson used a formula X crown Y. And the idea is that X indicates the total number of atoms in the ring, and Y equals the number of oxygens. Okay, so here we have 12 crown 4, where there are 12 atoms in the ring, 4 oxygens. 15 crown 5, and 18 crown 6. Now the unique properties of crown ethers to coordinate metal ions comes from the size of their cavity. So the larger the crown ether cavity, the larger the ion that's stabilized. And here is a picture of 18 crown 6. And this can accommodate a potassium cation in the cavity. And so here you can see from the electrostatic potential map, there's a higher concentration of negative charge, more partial negative, coming from the oxygens pointing inward. And if you look at the space-filling model, the potassium fits right inside that cavity. So this is a very interesting example of self-assembly and non-covalent interactions. Because of the unique ability to solvate a cation, there are many different applications of crown ethers in both synthetic organic chemistry and in medicinal chemistry. So this is showing an example of this reaction above when potassium fluoride is mixed with 18 crown 6 and benzene. What happens is that the potassium is coordinated in the center, and this will allow the fluorine to be released from the KF. Typically, KF is insoluble in benzene. When you can solvate a cation and release the F- so that it's soluble in benzene, it can then act as a nucleophile. Typically, F- will interact with a polar solvent when KF dissolves. Because the F- is not happy in benzene, but it is dissolved, it is free to act as a nucleophile, where it isn't as free to do that in typical reactions in polar solvents. If we look at example 14.4, it gives a series of reactions Here we have a bromine, and we're going to substitute it with a fluorine. And you have to figure out which crown ether you use. Now, the reason why I'm showing you this example is not because I need you to memorize the size of an internal cavity of a crown ether. But I'm using it to demonstrate that here, if you look, a sodium and a potassium. The sodium is smaller than potassium. So Na plus is smaller than K plus. So here what you need to know is that you need a larger crown ether, such as 18 crown 6. And here you could use a smaller one, such as 15 crown 5. It is interesting because some antibiotics, such as non-actin, which is shown here, behave similar to crown ethers. They can solvate a cation, such as sodium or potassium, and pass through the cell membrane. As a result, when the Na plus or K plus enters a cell through this manner, it will disrupt the gradient of Na plus and K plus in and out of the cell. And when the ion channel is disrupted, the cell will typically die and it interrupts cellular function. So these drugs are promising new candidates for killing bacteria as potential antibiotics.